So in this lecture, I will discuss the dual of the space of continuous functions defined on an interval AB. So let me consider X a metric space which will be compact. So a compact metric space. And let me define by Cx the space of continuous functions defined on F and taking real values. So this is the space of all functions f from x to r, which are continuous. Here I'm taking r. I could have taken the complex space, but let me fix it for the real functions. And let me define a norm in this space, which is the sup norm. So I'm taking the supremum for x in x of f of x. Well, we know that Cx, we have seen that with this norm, is a Banach space. So this is a norm. I leave it to you to check. And the space of continuous function endowed with this norm, it's complete. So it's a Banach space. So for what I said before, I need X to be a compact metric space. Now I don't need anymore this assumption. So in what I'm saying now, X, it's only a metric space. And I will represent by Bx the Borel sigma algebra. Of X. So this is the smallest sigma algebra which contains all open sets of X. And now let me define what's a sign measure. So a sign measure will be a function nu from the Borel sigma algebra to minus infinity plus infinity with the following properties. Well, I will require nu of the empty set to be 0, and I will require nu to be sigma additive So let me recall you what sigma additive means. It means that if I take Aj, a collection of sets in the Borel sigma algebra Bx, which are disjoint 2 by 2, that means that Aj intersection Ak is equal to the empty set if J is different from K. Then the measure of the union of Aj, it's equal to the sum of the measures. So this is the definition of a signed measure. It's a signed measure because it might take negative values. And, well, it has to give measure 0 to the empty set, and it has to be sigma additive, which is what I wrote here. So this is the signed measures. And the first remark is that if nu is a signed measure, then it cannot take at the same times the value minus infinity and plus infinity. So nu, either nu it's a function from the Borel sigma algebra to minus infinity plus infinity, or it's a function from minus infinity plus infinity. But the sigma additivity property tells you that you can't take nu, you can't find two sets such that one has measure minus infinity and the other has measure plus infinity. So nu takes either the values between minus infinity with plus infinity, or minus infinity plus. So just to fix ideas, I will assume that nu takes value only from minus infinity to plus infinity, including the value plus infinity. And for that, you have, let me recall, a theorem which is called the Han-Jordan decomposition is that if nu is a signed measure, then it can be written as the difference of two non-negative measures. So this means that there exist nu plus and nu minus, such that, well, nu plus and, well, nu plus takes values in 0 plus infinity, and nu minus values from 0 to plus infinity, but excluding the possibility of taking the value plus infinity. These are measures, which means that nu of the empty set is 0, and nu plus and nu minus are sigma additive, and nu can be written as a difference of nu plus minus nu minus. So the Hunt-Jordan theorem tells you that if nu is a signed measure, it can be written as the difference of two non-negative measures. So X is still a metric space. Bx, the family, the sigma algebra of Borel sets of X. And now I'm introducing the space Mx, which is the space of finite signed measures. So this is the space of all nu, which are finite signed measures, but which are finite, which means that nu takes value only between minus infinity and plus infinity, and that means that if I decompose nu as nu plus minus nu minus, so if I recall the Hunt-Jordan theorem, which allows me to represent this measure as the difference of two non-negative measures, what I have is that nu plus of x, it's finite, and nu minus of x, it's finite. So let me define what will turn out to be a norm. If I now consider measure nu in mx, which means a finite signed measure, I define by the norm of nu as nu plus of x plus nu minus of x. So this is a non-negative measure, and what I claim is that this is a norm. And moreover, if I take the space mx of finite signed measure endowed with this norm, well, this space is complete with respect to this norm, so this is a Banach space. So all these results can be found in a book on measure theory. I have now all elements to state what's called Riesz representation theorem. And the proof of this theorem, which I won't give, can be found in the book by S.J. Taylor called Measure Theory, or the book by H. Royden called Real Analysis. Now, in this theorem, X will be a compact, separable metric space. And in this setting, we define two Banach spaces. The first one is the space of continuous functions with the sup norm. And the second one is the space of finite signed measures with the norm which I defined as, I'll call that maybe the total variation norm. So what Riesz representation theorem tells you is that if I represent by Cx prime, and sometimes I will instead of prime, I'll call that star. But let's call it Cx prime as the dual space of Cx, which means the space of all bounded linear functionals on Cx, so that this space is exactly the space of finite signed measure, which means that if L it's a bounded linear functional from Cx to R, so a bounded linear functional, then there exists a finite signed measure nu in Mx such that L of f it's equal to the integral over x of f with respect to d nu, and this for all function f in Cx. So this means that all bounded linear functionals defined on Cx can be represented as an integral of f with respect to a finite signed measure. And the converse is also true. If you defined L by this identity, where nu is a finite signed measure, then L it's a bounded linear functional. So, and this provides you a representation of bounded linear functional defined on the space Cx. So we have this identity which tells you exactly what is the space, the dual space of the space of continuous functions defined on a compact separable metric space. So my lecture today will be to prove this theorem in the special case in which x is the interval AB. So I forgot to say that we have this representation, and moreover, the norm of the bounded linear function of L, it's equal to the norm of nu, which appears in this representation. So not only I can represent the bounded linear functional this way, but the norm of this bounded linear functional, it's equal to the norm of nu. And remember, this is nu plus x plus nu minus x. So as I said, I will prove this theorem in the case in which the compact metric space is the interval AB. So let's fix x equal to the closed interval AB. And in order to state the theorem, I need to introduce the space of bounded variation functions, which I will call BV or BVAB. So a function, let me call it u from a, b to r will be said to be of bounded variation if, so this is a definition, if the following holds. Let me take a partition of the interval AB. So T0 will be A. This is smaller than T1 up to smaller than Tn, which is equal to B. So this is a partition. Let me call this partition pi. And I will call the variation over the partition pi of the function u the following object. So this is just the variation of the function along this partition. So this is the sum of u tj plus 1 minus u of tj, and the sum runs from 0 up to n minus 1. So this is the variation of u along this partition. So I'll say that a function u belongs to the space of bounded variation functions in the interval AB if the supremum, so if there exists a constant C0 such that the variation of pi of u along the partition pi, it's bounded by C0 for all partition pi. So you take any n, any partition of your interval AB, you compute the variation of u along this partition, and this is bounded by a a fixed constant C0. So this is the space of a bounded variation function, and I will call the supremum over pi of v pi of u. So I'm taking a supremum over all finite possible partitions of the interval AB. This supremum will be called the total variation of u along the interval. And this is a norm. So this is the space of bounded variation functions. So I didn't mention, but let me insist on that A and B are real numbers, right? So A, it's smaller than B, and both are real numbers. So I introduced the space of bounded variation functions because there is a one-to-one relation between the space of finite sign measure on the interval AB and the space of bounded variation functions defined on the interval AB. And what is this one-to-one correspondence? Let me take nu, a finite sign measure on X. Then I will define a function rho t defined on the interval AB as follows. So rho t will be the measure. So maybe nu, this finite sign measure, gives a mass to the point A, and plus nu of the interval AT, which can be also written as nu of AT. If I define rho in this way, so rho now it's a function from the interval AB to R. It's R because I assumed that nu to be a finite sign measure. So I leave it to you to check that rho is indeed a bounded variation function. And this is very easy to check if you recall that any finite sign measure can be written as a difference of two non-negative measures by the Han-Jordan theorem. So this is one relation. If I fix nu, a finite sign measure, then I can define a bounded variation function through this equation. Now the converse also holds. So now let me fix rho, a function of bounded variation. And let me define by S, this is a semi-algebra. So this is the definition of this semi-algebra. I'll take all intervals of form CD, where C is less or equal than A. This is smaller than D and less or equal than B. And I'm taking that with the union of the sets A, D, where now A, it's smaller than D, smaller than B. So I leave it to you to check that S, it's indeed a semi-algebra. And I will define a measure on this semi-algebra by setting that nu of the interval CD to be equal to rho D minus rho C. And this for C between for A less or equal than C, smaller than D, less or equal than B. And nu of AD to be rho D. And I claim that nu, it's sigma additive on the semi-algebra. So that nu, it's a measure on S, on this semi-algebra. Then you can use the to extend nu to the Borel sigma algebra of the interval AB to R. So in this way, you construct a finite sign measure on the Borel sigma algebra. And what I claim is that as we had before, nu of the interval AT, it's equal to rho t. So if you have a bounded variation function rho, you can construct a measure through this procedure which use the Carré-Theodori extension theorem. And moreover, you have that nu, well, as it's said here, you have that rho t is given, or nu, the measure of the closed interval AT, it's given by rho t, and the measure of an open at A and closed at D, it's given by this difference. So this gives you the one-to-one correspondence between the set of sign measure and the set of bounded variation. And this is one-to-one, that what you can check. And we will need these correspondence in order to prove that the space of the dual space of the continuous function is the space of finite sign measures. So let me summarize. If I have nu in a finite sign measure defined on this interval, I can define the bounded variation function through this formula that rho t is equal to nu of the interval AT. And rho belongs to the bounded variation function. In the same way, if I have rho in the set of bounded variation function, I can define nu through Carré-Theodori theorem, but essentially what I said is that I state that nu of AT has to be equal to rho t for all t, and that nu of A or C D, it's equal to rho d minus rho c. This forms a semi-algebra, and then I can extend to nu to the Borel sigma algebra to Carré-Theodori. And moreover, we have that the total variation norm of this bounded variation function rho, it's exactly equal to the norm of nu. So we have also this identity, and again, all these results I just presented can be found in a book on measure theory. Now, here comes the theorem, which is the main result of this lecture. I want to prove that the dual of the space of continuous functions on AB, so that this is equal to the space of finite sign measures on X, on the interval AB, and we have seen that this corresponds to, there is a one-to-one correspondence with the space of bounded variation functions on X. And well, AB, it's of course a compact metric space which is separable, so this is a special case of Riesz representation theorem. But in this special case, the proof is quite elementary. So let me start with L, an element of CAB prime. So L, it's a bounded linear functional defined on the space of continuous functions. So L takes a continuous function defined in AB and gives a real number. It's linear and it's bounded. And from L, I want to find a measure on the space on X, finite sign measures, which allows me the representation that L of f, it's equal to the integral of f d nu in AB. So let's see what's the idea of the proof. if I can take f to be the indicator of an interval, so let me represent by qst the indicator of the interval st. So this is a function which at r is equal to 1 if r belongs to the interval st, so if s is smaller than r, smaller than t, and 0 otherwise. So, of course, this function is not continuous, but assume for the moment that, well, I can define L of f. So if I could do that, I will take the interval at. That would give me the integral from ab of chi at d nu. So this is nu of at, which, remember, the relation between a measure and a bounded variation function is given by this equation. So I would define rho t through this equation, and then I would prove that rho is a bounded linear functional. And once I have this equation, I will try to extend it to prove that L of f is actually equal. Well, to extend, I would extend this equation to this equation. If this is true for all intervals at, then by approximating a continuous function by linear combinations of such functions, I would get this identity. So this is the strategy of the proof. I want to find nu for which this holds. So in some sense, I will try to extend the definition of this bounded linear functional to discontinuous functions, to the indicator of sets. If I can do that, then I can define rho t, a function defined on the interval ab to r through this equation. Then I could try to prove that rho is a function of bounded variation. And if I can do that, I would have this representation with a function of bounded variation. Then the next step will be to try from this equation to obtain that equation by approximating a continuous function through linear combinations. And once is that, this is exactly what we wanted to prove. So this is the strategy. I'll first try to extend the definition of L to indicator functions. Then I will introduce rho. Then I'll prove that rho is of bounded variation. And finally, from this equation, I'll try to get that one to find a representation of my bounded linear functional L. So let's try to follow these steps and to prove the theorem. So I have L, which is a bounded linear functional from space of continuous functions to R. As I said, I want to define L of an indicator function. So let me represent by B of AB. So let me call this set Y. So this is the set of functions H from AB to R, which are bounded. So the bounded functions defined from AB to R. So this space, it's a normed linear space, and I will call it Y. And this defines a norm. So it's a normed linear space with this norm, and as I said, it's Y, and of course, X, it's a linear subspace of Y. Now, I have a bounded linear functional defined on X. The Hahn-Banach theorem allows me to extend this bounded linear functional to the space Y. X, it's of course this space, right? I'll represent by X. Maybe it's not a good notation because X was representing the space, metric space before, but okay, let me call X now the space of a continuous function defined on the interval AB. So X, it's clearly a linear subspace of Y. I have a bounded linear functional defined on X. So the Hahn-Banach theorem tells me that we can extend this bounded linear functional to Y. So let me call the extension capital L. So L is now a bounded linear functional defined on Y. The norm of L, it's equal to the norm of L. And L, it's an extension, which means that LF, it's equal to LF for all functions f in X. So for all continuous functions f. So I just use the Hahn-Banach theorem to extend the bounded linear functional small l to Y in such a way that the norm is equal and it's an extension, so this identity holds. So I just recall what we did. We started from a bounded linear functional defined on X, the space of continuous function, and we used Hahn-Banach to extend it to Y, the space of bounded functions, in such a way that the norm are equal. Now it's very nice because the indicator functions belong to Y. So remember that chi at, it's the indicator function of the interval at. This is a bounded function, so I can apply L to this function, and I can define in this way rho t. So now rho, it's a function from the interval AB to R. Mind that if this bounded linear function were positive, which means that if considering positive functions I had a non-negative value, we could try to prove that this property is transferred to L. And if this was the case, I would get that actually this function, it's non-decreasing. So it's an increasing function because I could write, well, if t is larger than s, I could show that rho t is larger than rho s. But I'm not assuming that now, so I won't discuss this matter further. I just introduced this function rho, defined on the interval AB to R, and what I want to prove is that rho, it's a bounded variation function. So this is the first step, an important step in this proof. So to prove that rho is a bounded variation function, I need to estimate its variation on a partition. So let me call pi a partition, so that will be t0, which is A, smaller than t1, smaller than tn, and this is B. And I need to obtain a uniform bound on rho tj plus 1 minus rho tj, where j runs from 0 to n minus 1. I need to show that this sum is uniformly bounded over all partitions by a finite constant. So in the previous take, I defined rho through this identity. Pi, I consider pi a finite partition of the interval AB, and I need to estimate this quantity. So for that, let me introduce the sine function. So S will be a function defined from R to minus 1, 1, so that S of R, it's either equal to 1 if R is larger or equal to 0, and minus 1 if R it's less than 0. So this is the sine of R. And let me define by SI the sine of this difference. So SR will be the sine of rho tj plus sj, tj plus 1 minus rho tj. Because I want to get rid of the absolute value, so in the way in which I can get rid of is just saying that, well, this absolute value is actually this difference multiplied by its sine. So with this definition, I can rewrite this sum as rho tj plus 1 minus rho tj times sj, right? Because you see that, well, if this is positive, sj is 1, and which means that this multiplication gives you the absolute value, while if this is negative, then sj is minus 1, and which also gives you this identity. So this is perfect, because now I don't have the sign, the absolute value anymore, so I'll be able to sum these expressions. So let's first recall the definition of rho tj plus 1 minus rho tj through this identity. So this is j from 0, the sum from j from 0 to n minus 1 of chi L of chi A tj plus 1 minus chi A ti. And this is multiplied by sj. So now I can use the linearity of L to rewrite this as a sum in J of L. Okay, let me go very slowly. Sj chi A tj plus 1 minus chi A tj. So this is the function which is equal to 1 from A to tj plus 1. This is 1 from A to tj. So the difference will be a function which is 1 in the interval tj open to up to tj plus 1 times sj. Here I have a sum. I can use again linearity to put the sum inside L. So this is equal to L of the function from 0 to n minus 1 of sj q chi tj plus 1. And so you see that this function here, so let me call this function the function u. So let me erase the definition of the sign, just to make this precise. If I call u the function sum j from sj q tj plus 1, remember that sj it's either minus 1 or plus 1. This is a function which is 1 in this interval. So this function u has norm bounded by 1. Its infinite norm, it's bounded by 1, because well, this is either 0 or 1. This is either 1 or minus 1. And therefore, since L it's a bounded linear functional defined on the space of bounded function, we have that this quantity, the absolute value of this quantity, is bounded by the norm of L times the norm of u, but the norm of u it's bounded by 1. So this quantity here, it's actually bounded by the norm of L, because the norm of L, capital L, it's equal, we have seen, to the norm of L. So I obtained a bound which doesn't depend on the partition and which bounds the variation of rho along a finite partition of the interval AB. So this tells us that rho is actually a bounded variation, a function of bounded variation, and that the supremum, so the norm, the bounded variation norm of rho, it's bounded by the norm of L. So what we just proved is that if I define rho through this formula, then rho, it's a function of bounded variation, and its norm, it's bounded by the norm of L. So in what follows, I will need to integrate a continuous function f with respect to a bounded variation function, dt rho t. So you can do that, and this is called the Lebesgue-Stieltjes integral, which you can find again in any book in measure theory. So you need to know or to recall what is the Lebesgue-Stieltjes measure of a continuous or a bounded function with respect to bounded variation function rho. And by the way, this is exactly equal to the integral of af d nu, where nu is the finite sign measure associated to the bounded variation function rho. So now what I claim is that for any function in x, which means for any continuous function, then L of f, it's equal to the integral of f ab with respect to d rho, or which is the same with respect to, as I said, to the finite side measure associated to rho. And since f is continuous and capital L it's an extension, actually by proving that, what we proved is that LF is given by this integral or this integral, so that, mind, you have the representation which we are trying to prove. So what I'm claiming is that this identity here holds. And what we are going to do, well, we have the definition. So let me give you the idea. We have that chi st, or maybe let me put it a, that this is equal to rho t. And as I said, we'll try to approximate the continuous function f by linear combinations of these indicator functions. So let's fix a function f, a continuous function, and let me define h. So h of t will be defined according to a partition. So let me introduce a partition pi, which is again a equal to t0, smaller than t1, smaller than tn, and this is b. So this is a partition of your interval ab, t1, t2, up to tn, and this is t0. And what I'm going to do is I'll just take the value of f on the left-hand side of the interval, and I will define this function to be constant according to this value on this interval. So in the first interval, it will be closed on the left and close to the right, but in an interval tj plus 1, it will be open and closed, and the value on this interval will be dictated by the value of f on the left-hand side. I could have taken the right-hand side, it doesn't matter, but let's do it in this way. So ht, it's equal to f of a in the interval a t1, and then the first interval is slightly different because I'm taking a in the definition, and then f, it will be given by f tj on the interval tj plus 1, and now j runs from 1 up to n minus 1. So this is the definition of my function h. And what you can check is that if you take, so h depends on the partition pi. So now if you make the partition pi finer and finer, what you can prove is that in the infinity norm, h pi converge to 0 as the length of the partition, say that as the size of these intervals converge to 0. So let me call norm of pi the max of tj plus 1 minus tj. Since f is continuous, as these max converge to 0, h pi converge to f in the infinity norm. On the other hand, so this tells me, since L it's a bounded linear function, it's continuous, and therefore L of f it's equal to the limit as the norm of pi goes to 0 of L of h pi. So now what I will do is I will compute L of h pi to get the value of LF. So I fixed a continuous function. I introduced this approximation of my function f, and we know that L of f it's equal to the limit as the norm of pi goes to 0 of L of h pi. So what I need is to compute L of h pi, the limit of L of h pi. So here is the definition of h pi. I will write this as fa chi a plus the sum from 0 to n minus 1 of f tj chi tj plus 1. And now I'll just apply the definition. So I'll take L of h pi. So this is L of this quantity. Now by linearity, this is equal to the limit as the norm of pi goes to 0 of, by linearity, this is f of a, L of the singleton a, but if I look to the definition, this is taking t equal to a, so this is rho of a. Then I have a sum of ftj, then L of this indicator function, but this indicator function can be written as the difference of two indicator functions, and for that I get that this is h rho of tj plus 1 minus rho of tj. And so this is essentially a Riemann approximation of the integral, and by the properties of the Lebesgue-Stieltjes integral, since f is a continuous function, this expression converges as the mesh or the norm of pi goes to 0 to the integral from AB. So I'm taking A, so this will give me f of A times the mass at A, and this will give me the integral removing A from the integral, so of f d rho. And as I said, so this is also the integral of f with respect to the finite sign measure associated to rho. So here we have exactly the formula which I claimed, that for any continuous function, LF is actually the integral of f with respect to this bounded variation function rho in the interval AB. So this first piece gives me the contribution of the point A, while this other one gives me the integral from the interval open at A and closed at B of f with respect to the rho. So we just proved that since capital L is an extension, we just proved the formula which we wanted, that L of f is indeed equal to the integral in the interval AB of f with respect to d rho, which is the same as the integral of f with respect to the finite side measure nu associated to the bounded variation function f. So we proved in the previous take that for any continuous function f, L of f, it's equal to the integral from ab of f d rho. And again, let me insist from the fact that we're taking a, so if you wish, this is fa rho a plus the integral from ab of f d rho. Well, now we also proved that the total variation of rho is bounded by the norm of L. What I want to prove is that the norm of L is bounded by the norm, the total variation of the function rho. So in order to prove that, let me take a function f in x, so a continuous function. We need to estimate L of f. By this formula, f of L, it's equal to the integral in the interval ab of f d rho. Now again, I will use the bound from measure theory, which tells me that this quantity, it's bounded by the L infinity norm times the total variation of rho. And, well, this inequality tells me exactly that the norm of L is bounded by the norm of rho, the total variation of the bounded variation function rho. So, therefore, we have proved the representation of a bounded variation of a bounded linear functional through this equation, and we also proved that the norm of L is exactly equal to the norm of rho. So this gives you the proof of the representation theorem, and I will just show that if L is given by, so the converse statement is that any functional given by this identity, it's a bounded variational functional. So let's prove the converse. Which means that consider a function rho of bounded variation. Define L of rho on the space of continuous functions to R by the following relation. L rho of f, it's equal to rho a fa plus the integral from in the interval ab of f d rho. Then I claim that L of rho is an element of x prime, so it's a bounded linear functional defined on x, and that the norm of L of rho is equal to norm of R. Well, so let's prove that. It's clear that L rho is linear, and it's also bounded by the computation I did in the previous take. So in the previous take, from this formula, we concluded that the norm of L rho is bounded by the norm of rho. So what remains to be done is to show that the norm of rho is bounded by L of rho, and this is what I'm going to prove now. So to prove that the norm of rho is bounded by the norm of L of rho, observe the following. So I'll repeat the first part of the proof. I'm started from L of rho. I will extend L of rho to capital L of rho, which is defined on the space of bounded functions. Once I defined this L of rho, I'll define a function lambda t, which is L of rho of the applied to the indicator function of the interval at. So we proved that lambda is of bounded variation, and that the bounded variation of lambda is bounded by the norm of L rho, which is equal to the norm of small l of rho. So this is by the first part of the proof. Moreover, by the first part of the proof, we also know that L rho of any function f is equal to the integral from a to b of f d lambda. But we also know that this quantity is equal to the integral from a to b of f with respect to d rho. From these two identity, we conclude that rho is equal to lambda, that these two bounded variation functions are identical, and therefore that the total variation of rho of lambda is equal to the total variation of rho. And so this completes the proof. So what did we prove? We proved that any bounded linear function on the space of the continuous function of the interval ab can be represented by a bounded variation functional through this equation, and that the norms are equal of these two objects. And also the converse, that if rho is a bounded variation functional, then this formula defines an element of the dual. So actually, we proved that the dual space of the continuous function on the interval ab coincides with the space of bounded variation of functions defined on the interval ab, and we know also that this space coincides with the space of finite signed measures defined on this interval. So we proved Rie's representation theorem in the special case in which the metric space is the interval ab. So let me summarize what we just proved. We proved that the dual space of the continuous function defined on the interval ab is equal to the space of bounded variation of function defined on the interval ab, and we have seen that this space coincides with the space of finite signed measures defined on the interval ab. So what exactly we proved? We proved that if L is a bounded linear functional defined on the space of continuous functions on the interval ab, then we can find a bounded variation function rho such that L of f is given by this integral for all continuous function f. And moreover, the norm of L is equal to the norm of rho. The converse is also true, that if you fix a bounded variation function rho in the interval ab, and if you define by L of rho for a continuous function f by this integral, then this functional is bounded and linear, so it belongs to the dual space, and the norm of this functional is exactly equal to the norm of rho. So this is the Rie's representation theorem in the special case in which the compact metric space is the interval ab. Just a remark, in all this lecture, I consider intervals of the form ab because what I have in mind is that these bounded variation of functions are right continuous. Right? If you have a bounded variational functional rho, a theorem tells you that you can write rho as the difference of two monotone functions. So rho can be written as a function f minus a function g, where both f and g are non-decreasing functions. If you have f and g a non-decreasing function, you can define them, turn them into right continuous or left continuous function. So I chose here to take them to be right continuous, and for these reasons, I consider intervals of the form AB open at the left-hand side and closed at the right-hand limit. So you could have chosen to define them differently, but this is a choice which has been made and which I didn't mention before. Then I want to conclude this lecture with an example. So let me fix an interval AB, and let me consider a function h, which is in L1. So h is integrable, and now I want to define L of f. So again, f now it's a continuous function. L of f as the integral of f with respect to h in the interval AB. So I claim that L belongs to, of course, to the space, to the dual space. So it's a bounded linear functional, and that the norm of L is, in this special case, equal to the H1 to the L1 norm of H. So let's prove that. Well, it's clear from this. Well, this is well defined because f is bounded and H belongs to L1. It's linear, and L of f, it's bounded by the L infinity norm of f times the L1 norm of H, and therefore this implies immediately that L, it's bounded by the L1 norm of H. So what I really need to prove is that the converse inequality hold. So what remains to be done is to prove the converse inequality so that the L1 norm of H is bounded by the norm of L. So in order to do that, let me define rho t as L chi AT. So remember, in the proof of the Riesz representation theorem, we started from this bounded linear functional. We extended it to a bounded linear functional defined on bounded functions, and we introduced this function rho t, which we proved to be of bounded variation. And not only that, it's that once we introduce that function, we have proved that for any continuous function f, we have the following representation. L of f, it's equal to the integral from, in the interval AB, of f d rho. Now we also have this equation, so we have this identity for all continuous functions. So this means that for all continuous function f, the integral from AB of f d rho, it's equal to the integral from a to b of f h dt. So this is telling us that the measure, the finite sign measure generated by rho, is absolutely continuous with respect to Lebesgue, and that its Radon-Nikodym derivative is equal to h. Or in other words, if you wish, that rho t is actually equal to the integral from a to t of hs ds. And from this identity, well, we know that L, norm of L, we also proved that once we introduce this bounded variational function, the norm of L is equal to the norm of rho. Well, if rho has this special formula, which means that if rho is absolutely continuous function, the bounded norm of rho, it's equal to the H1 norm of H, the L1 norm. Sorry, with H I'm always saying H1, but when I want to mean L1. So if rho is given by this expression, then you can show that the bounded variation norm of rho is actually equal to the L1 norm of H. So since we have this identity, we get immediately that indeed the norm of L is equal to the L1 norm of H. So what we just proved or showed is that if you now have a function h which is in L1 and you defined a functional in the space of continuous function through this identity, well, this functional, it's linear, it's bounded, and therefore it belongs to the dual, and the dual, the norm of the dual, is given by the L1 norm of this function h.